Have you ever seen Python say like error? Have you ever seen something that looks like value error? Or how about index error?
All the time.
Yeah. And those types of things, well, you know, there's different types of errors, I guess. But, and we'll go in far more detail about exceptions next semester. At this point, I'm showing you what they are to give you an idea of why they're important. And some exceptions are caused by the programmer misusing something. And other times, like, exceptions can be caused by exceptional situations. They're not always necessarily an error. It's just something funny happened. So, yeah, we're not going to go into too much detail, but chances are you've seen value error, index error, and there's a lot more of them, and you can make your own. So, if we look at this code, int hello, I'm trying to convert the word hello, the string hello, into an integer. And Python goes, what? That's not a thing. I can't do that. You asked me to do something that I just can't do that. And that seems reasonable, right? Because if I ask anyone in here, hey, convert your name to an integer, you're going to be left going like, well, okay, can you be more, like, how? How do you want me to do that?
I mean, you didn't tell me how, I just did it the way I want to do it.
Exactly. And Python, the way Python wanted to do it was to not do it. So, and then if I try to index a list, index 11, well, list index out of range. Why? Well, because there is no index 11. It's not there. There's nothing there, so it's saying like, yeah, we got a problem. So what's neat here is, like, when I say int hello, someone wrote the code that's under that hood that would be converting a string to an integer if it could, right? And someone wrote the code, like there's rules and there's code somewhere about how to index lists. You didn't write it, you didn't look at it, but it exists. Someone wrote it decades ago, okay? And here's the thing. If you're using, and listen up, because this is an important idea that people, if you don't get this idea, you're going to be left going like, but exceptions seem silly. The idea is, when someone wrote this code 20 years ago, and they knew, well, someone might try to convert a string to an integer. And that's probably not what they want to do. And so I'm not going to do anything. But here's the funny thing, is if someone 20 years from now, using my code, 20 years ago, I'm the guy 20 years ago writing the code, someone using my code in the future might want to handle the situation a specific way. If someone wrote a program, and maybe they get user input from the program, where it's like enter a number and you enter your name. What should my code do today to deal with the scenario that you're going to have in the future? The answer to that question is, I don't know. But here's what I do know. I can make a special thing called an exception and throw an exception. Then, if you're the programmer using my code in the future, and you ever see this exception, you will manage it however you want. Do you want the program to just say okay, try again, that's not a number? Or do you want the program to crash immediately? Do you want it to just carry on and ignore the problem? There are a lot of options we could do. It depends on what you want to do. But how could I know 20 years ago what you would want to do today? And what you want to do today might be different from what they want to do today from what they want to do today. So it's kind of like the programmer of the code you're trying to use is saying, you're trying to ask me to convert hello to an int. No, can't do that. But that's not my problem. I mean, it's my problem in the sense that, yeah, I can't do it on my end. But if this is a problem you're dealing with in the future, this is something that you have to figure out. You have to manage this. So they told their code to raise an exception. That's what happens. They raise an exception and throw it. And then you could catch an exception to deal with it however you want. Here's an example of a silly little function called do not give me 5. If you give this function any number other than 5, it's fine. It's just going to print out the number. But if you give it 5, it'll raise or throw this exception. See, I called it with 4. 4. In fact, try this yourself. Go down here, paste it, and then do not give me 5 4, okay, 6, 5. We got an issue. Because if I wrote this code, and you're using this very important function in the future, and a 5 somehow gets pushed in as one of the parameters, well, what do you want to do about it? I don't know what you want to do about it today. I don't know, like, what are you going to want to do about it in the future? I don't know. So, that's obviously a rather silly example. But how about this one? Divide. Here's a much better example. Oh, what did I do wrong? Did I not run it? Oh. Oh, that's still not right. There we go. Great. But of course, dividing by 0 is kind of a funny little exceptional scenario, right? You're not supposed to do that because it doesn't really make sense. So if we put in a 0, it throws an exception. 0 division error, and I added the message no. This is already a built-in type of error, by the way. There's a bunch. Don't worry about memorizing them. No one would do that. So we can throw an exception here because I might be writing a program that reads in values from the environment maybe. Maybe I'm like a sensor. And that sensor, it's reading in all those values and it needs to do division all the time for whatever reason. But every once in a while, that sensor, because of its precision, reads in a 0. And then you try to divide something by 0, we got a problem. But again, if you're trying to divide by 0, and I wrote the code divide here, what do you want to do? Does it not matter if it happens and that sensor sees the 0, tries to divide by 0, and then we raise this exception so you see this exception? What do you want to do about it? Do you want to just skip it and ignore it and be like, okay, great, okay, just carry on as if everything's fine? Or maybe you want your program to stop running immediately because that means something bad's happening. I don't know. That's for you to decide. So when I raise an exception in my code, I'm passing you a message. I'm letting you know something funny happened. The something funny is exceptional. It's rare. So all of the code you're writing that you've seen so far, that's like your functional working code working. And then this whole idea of an exception is in a way to separate those like funny scenarios into a separate idea, these exceptions. And then if something funny happens, I give you this exception, you have it, and now you know something funny happened, and you can deal with it. Great. So we can throw exceptions or raise exceptions. Every programming language has a slightly different word they use to mean the same thing. So we can raise an exception. So if you were writing code that would then use blah, 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 code that could raise an exception, like divide, or in this hypothetical one called function that can raise exception, If I know that this function that I'm using might be throwing that exception for me, what I can do is I can say, try to do it. If everything works fine, great. But if something funny happens, if we ever see an exception, I have this separated code set aside that'll run only when the exception's there. It's kind of like an if statement, kind of. It's like an if for the exception. Run this, and if something went wrong, you deal with it. So what do I have here? I got a bunch of examples. Okay, I can't divide 9 by 0. So what should I do about it in 1999? Well, you're writing a program right now trying to use the function to do something. How could I know how to handle the situation in your program? How about this? I write some code in 99 that says something exceptional happened, and then I let you know that something funny happened. That's the whole idea here. So we try to do it, and if no exception's thrown, it skips everything in that except block. But if an exception is thrown, then we go into and run that except block. So let's look at a couple examples. Here's Jane, for example. Jane wants us to set the result to not a number. NaN is kind of another special value in computers. That means not a number. So if you have like an integer, that's like it's an integer type, but it's not a number, if that makes any sense. Let me show you. If I can remember how to do an example of this in Python. Print, okay, a equals int. I think this might be it. No. How do I do nan? I guess I have to do float, lowercase. There. Okay. Print a. There. So we're printing out A. Wait, print type A? What? That doesn't make any sense. There. It's not a number, but it's a float. If this seems funny, it kind of is. But sometimes if you're running some calculations and you try to divide by 0.00000000001, so it's technically possible. The problem is the value that you're going to get is going to be so big that your computer can't represent it. So it might just say like, okay, not a number. It's a float. It is, but I can't really do anything with it. So it's a special type of float. Don't worry too much about it. But this might be something reasonable someone might want to do. Where if I try to divide by 0, instead of crashing, I will just say, okay, whatever, the result is not a number. Yeah?
Are all other numbers the same?
Let's check. To test this idea, we'd have to be a little bit more rigorous than what I'm about to do, but I'm going to check it very superficially. I saw an example of me doing that. But I'm wondering, that is interesting. They look like they could be, but I guess they're not. And this is probably by definition. Because to me, you raised the question of like, are they the same? Because I guess if you're checking if two numbers are equivalent, is 1 equal to 1? Well, when you have something that's not a number, maybe it's good to just say they're not the same because we don't know what they are. I guess that's probably like the convention they're following. Interesting question nonetheless. So yeah, here's Jane's code. She wants to divide by 0. So she gets two numbers, she calls divide, and if she sees a zero division error, she sets the result to not a number. And then she returns that value. So now her code is fine. It won't crash, it'll still operate. I don't know how not a number would affect the rest of her program. But the point here is she got an exception, and what she wanted to do was just set it to not a number and carry on. Then we got Bob. Bob just wants to have his program keep doing its thing. So Bob will do it. Oh, wait, no. Bob just wants to have his program keep asking the user for the input until it can divide by those numbers. So have a look at this code. We read in numbers, we divide by 0, and if it works, we leave the loop. If it doesn't, if we catch the exception of 0 division, we say bad input. And the loop just keeps going. So this is an example of just, if it didn't work, try again. So that's what Bob wants to do. Jane wanted to just set the result to not a number. Bob wants to just be like, okay, just keep trying until it works. And then we got Tim. Tim's got some medical equipment, very, very, very important medical equipment that works with radiation and stuff. And if it tries to divide by 0, if something exceptional happens, because this is potentially dangerous medical equipment, if something peculiar happens, I want the program to stop running immediately. Crash. Stop. So I'll say, if I see a 0 division error, exit. Exit is a way to just say, stop the program. So now we've got a third option. The first option was not a number. Second was just keep going. Tim wants it to crash. And then Sally has code for a helicopter that needs to do all these calculations. And Sally doesn't want the program running her helicopter to crash if she's flying a helicopter. She's going to just be like, all right, just carry on. Kind of like the example of like the sensors. If we see something that doesn't work, just carry on. It doesn't matter so much. So in this scenario, we catch the exception, but it doesn't really affect the running of the program. We just take note of it and carry on. So these are 4 options. But again, when I wrote this code, and what did I say, 1999 for divide, I don't know what Tim, Bob, Sally, or Jane want to do. They know what they want to do in their peculiar scenarios. I don't. Are there any questions about this idea? Yes?
Well, what's the difference between break and exit?
So break breaks out of the loop. So if you have a loop and you see break, it'll just exit the loop and continue writing the program that's following the loop. Exit means just stop running the program entirely. Yeah?
So you literally just type in like except like if there and it'll just stop it basically.
Yeah.
Okay, that's really good.
Yeah. Although, like, you might think, oh, great, cool. I've used this like once in my life. So twice if you count this. It's not a very common thing I use, but I don't know, for whatever reason. Any other questions? So there are a lot of exceptions. I'll skip over these details, but it's really great because it allows programmers to pass information around and communicate through time, right? Like I can throw a message to you from the past, basically saying my code that I wrote in the past, something funny happened that you need to deal with today. Does it make sense? Do you have other questions about exceptions? We're going to go into more detail on this next semester if you're in 162. And we'll learn more about the nitty-gritty. You can make your own exception types and everything as well. But, yeah, exceptions are pretty neat. All right. Objects. This is, of all the topics left in the course, the next following topics are objects, and then more on objects, and probably even more on objects. Then we talk about searching, but we've already been doing linear searches for ages. And then we do sorts. Sorting is a very big topic. Do not get me wrong. Sorting is a big one. But objects, I would say, is the last really big, beefy, new idea that we're going to learn this semester. I'm going to warn you, though, it kind of requires you to like flip a switch in your head, because we haven't been making our own objects yet. You've been using them, like it or not, you have, like the lists and NumPy things and the strings and all that. You've interacted with them. Objects have like methods, right? They have attributes. So you've been using them, and what's cool is you can make your own. You can make your own object. So, for better or worse, you're going to have to get used to them, because object-oriented programming is very, 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 very popular and common. All of like the big, important, popular languages are object-oriented able. So, a lot of stuff that we as computer scientists we like logical encapsulation. And if you remember what that word means, it's like, if I've got a chunk of code that does something kind of like as like a logical unit, I might make it a function, right? That's not a crazy idea. Linear search, sure, I could write the code in line, but I could also make it a function, because linear search is kind of like this nice logical unit of stuff. Unit of instructions I care about. And then objects kind of let us take it a step further. So when we have encapsulation, it allows us to think more about the what as opposed to the why. If look, I know you wrote code to do a linear search. I know you wrote it. But you write it once, you know it's correct. Now, any other time you want to do a linear search, you just call your function linear search. You don't have to rewrite everything. So you don't have to think about the nitty-gritty in there anymore. You can just think of the operation you're doing as linear search. You don't need to think of your linear search anymore in your bigger piece of code of like, okay, first I need to go through everything and then do this. Well, yeah, that's the linear search. But it's almost like the units of steps that you're thinking of, the units of instructions in your code and your algorithms kind of can get condensed, right? Like linear search, I don't have to write it all anymore. I can think about it as, I'm going to do a linear search here. Instead of saying, I need to look at all the elements in there, and then for each of them, I need to compare each one to the other. And if I find it, I'm great. Like, okay, that's fine, that's great. And yeah, I know you know that, but you don't need to think about the under the hood anymore. Just like print. You don't need to think about what's under the hood. There is a lot going on in the back of your computer when you say print hello world. There is a lot. But you don't need to think about that. So in your code, when you're writing your code, you don't think about all those steps. All you think about is, I just want to print something out. So you say print. Beautiful encapsulation. And it's an example like this. It's like, do you know how to turn on your car? Yeah, I do. Do you need to know how every single thing inside your car, how it works in order to use your car? No. I don't need to know how the print actually works in order to use it, which is great. Now, mind you, we're computer scientists, so we are going to learn about what's under the hood. So we will learn about all the bits and bobs under there. But in principle, we don't need to be concerned about that all the time. For example, there are a lot of layers of abstraction we can think about a car. We could think about, okay, wow, we got a 4-stroke engine there. Or, we can think of it as its parts. Like here, I'm thinking about the parts and the mechanics of the engine itself. Or I can kind of take a step back and be like, well, okay, yeah, sure, all of the pieces in the car have their own components inside of it. But I could also think of the car as like the collection of bigger pieces. Like we got the engine, we got the battery, we've got this, we've got that. Or I can think of it as turn on the car. Hit the gas, hit the brake, right? These are different layers of abstraction. different levels of detail. It's like the resolution of detail you're looking at. We can go all the way down. And we can play this game forever. Right? And we can play this game forever on the computer. Well, okay, when you wrote this code, like how did the print work? Well, okay, print worked by doing this, that, and the other. Well, how did that work? Well, it set the zeros and ones to make it work. Well, why does that work? Well, the zeros and ones represent low voltages and high voltages that get pumped through your processor to do everything. Well, how does that work? We can play this game forever to go down to like atomic units, right? But we don't think about it like that. Back at the beginning of the semester when we were talking about like, when you make pasta, how do you do it? How would you tell someone to make pasta? You'd say, okay, boil water, add some salt, throw it in and wait 10 minutes, right? That's what you do. But we can play that game where we just keep going down further and further and further and further and further into more and more detail. We can go all the way to the detail of like firing axons in your brain and your neurons are communicating to move your tendons and muscles and everything. Yeah, okay. Who here thinks about moving their tendons and muscles when making pasta? No, that's not a thing. We don't have to do that, thank God. So objects and abstract data types. So now we get to make up our own stuff. You've used integers, strings, floats, booleans. We can make whatever we want. We can make humans, cookies, cars, whatever we want. You get to say what the data is and what it looks like. You get to say how the data will act, and you will get to say what you'll do with it, how you interact with it, and everything. You are now God. You are inventing it. And one of the hardest things that students have at this stage is when I'm like, okay, you get to make your own objects. And they're like, well, what do I want to do? Whatever the hell you want to do. You can make it whatever you want. And it'll work if you do it right. So NumPy arrays, those were objects. Whatever. We'll skip over that. The point is, you can learn how, blah, blah, blah. Okay, implementing objects and abstract data types. Those other details, they're interesting, but not too important right now. So, now that we're motivated about, okay, abstraction, like the NumPy array, there's a lot going on under the hood. But I am fortunate enough to just be able to interact with it in such a simple way. But there's so much going on under the hood. I can interface with my car so easily relative to all the mechanics and systems at play under the hood, right? There's that separation. You've been using lists. There's a lot of mechanics under the hood, but you just like make them and then append to them and whatnot. Great. So we can make our own objects. And to do this, we make a class. The word class is a description of what an instance of that class could be, an object of that class could be. So I could define a class for enthusiastic students. Right? I want to make an enthusiastic student object. Why? Because. And feel free to follow along. How about we actually end here today? How about that? Yeah. Because we're going into the break, and I don't want to start teaching you the new big idea, and then you leave for a week. So we'll end here. Are you okay with that?
Yes.
All right.
100% okay.